So with that infrastructure, one of the main concerns we've had is always with data, and it's with the heavy compute that we need to process the data, particularly with moving the data between devices. So this talk really isn't about the CD7, it's not really about the CCI, but everything that I cover will come to benefit. So not just that goes to that instrument in this facility, but it comes across to all instruments in all facilities. So with that in mind, we requested almost $500,000 from the faculty, and strangely enough, they give us all of the money, which was quite a surprise. And we've recently gone for a tender, and we've had that awarded to XMA and Supermicro. So within that, we purchased a good chunk of storage and a good chunk of compute, and you're going to start to see that coming online over the next few months. Part of this, you're already going to see some of the work we're doing behind the scenes, which is, for those of you who work at Nuffield or using the Nuffield instruments, you'll have seen that work going on, which is the isolation of the machines, the disabling of USB and bringing them back onto the network. It's very common to what already happens at the bioscience building, but this is happening across all of our SRF, not just the CCI. So just to explain what that change looks like, because I know it's not always easy to understand. Previously, with Nuffield, all the instruments were off the network, and you had to use USB devices. This is very different to biosciences. So what we're changing is no matter what instrument it is, it will be on the network. You will not be able to use USB. It must go through the storage system. From the storage system, you can then access it. So it's very common so if you're already using like CCI or 2. The bigger change is we're adding a HPC system onto the side of this. It's going to be tightly coupled to the storage system and very close to the instruments themselves. So when I talk about HPC, there's always a question of what does that mean? So HPC, just to have it for the very basic, is high performance computing. When we talk about HPC, that word tends to get thrown around quite a lot without a strong definition of what it is. Sometimes we just think of it as a very big workstation with lots of RAM and a GPU and such forth, just bigger than our standard desktop. When we talk about HPC, traditionally, what we really mean is a series of high performance computing systems that we tightly couple together. We also look at having a very high performance storage system that again is tightly coupled to the compute platform, and between the two we have very fast networking that's very low latency, so we can do very big data processing very quickly. And specifically, what you'll tend to find that gets a bit more difficult for users is that you tend to need bespoke software that will work across those nodes. That's usually where people get scared, which is fine. But what you can also get if software is very simple enough that it's what we call embarrassingly parallel, which tends to be what imaging data is, because when we look at an image, we tend to look at one image and we process that image, and then we look at the next image and we process that. So we can kind of spread that workload across. So we will use what's called job scheduler, and that just distributes that workload for us. So I'll come back to that later on, but just for now, just to explain what we've purchased so you get an idea of the scale of this. We purchased 1 petabyte of storage already, and we're due to purchase another petabyte. They look like these nice little machines. There's about 24 disks in every system, and we bought a few of those. The storage will be aimed to be reliable and highly available, so wherever you go, it should always work, but don't hold me to that. And it's all going to be located here in Liverpool. I think we're facing the wrong way, but it's basically going to be located on campus. So it's almost central to all of the microscopes and all of our SRF facilities. So the performance should be fantastic. One of the things that I'm particularly keen on, which I believe is something that our research IT team should be keen on, is we try to avoid vendor lock-in. All of our systems will be built within open source. They'll all be managed in-house. What that means is we can try to resolve and fix things, and we can customize things to meet the research. And we can build on any applications on top of that, which is fine, but the core of this will be very much open and very much dynamic to whatever our needs are. When we have this system, what will be coming into place is essentially project storage, and it's very similar again to what you get with CCIO2. The idea is you can request, let's say, minimum, I think we're aiming for is a petabyte of storage, a terabyte of storage, not handing out a petabyte each. Going to be handing out a terabyte of storage each per project, and the idea is that terabyte is you can pass it between facilities. So if you traditionally do LM work and then you go over to EM or you go to any other facility, you can pass that imaging along, and at the end of the process, when it comes to data analysis, you'll have all the data in one place. And I think this is probably great for some of the EM work where they want to see your LM work to figure out what you actually want to find. And that data is just going to be available for you to share with colleagues and hopefully externally. You'll be able to access it from home, from your office and such forth. And the second part of this is our core compute. So again, just to explain the scale of this, so the core compute is going to be directly attached to the storage. It's going to have 100 gigabit networking. The chances are, I'm really hoping, is you won't be able to saturate that level, considering we're starting from 1 gigabit at the moment. So it's quite a bit of a leap. And again, this is going to be a completely scalable platform, and it's going to be completely vendor neutral. So we've just got basic Linux systems underneath that do very little. We're just going to build all the applications on top of them. In terms of the size of this, and I use the term CPU cores very ambiguously. What I refer to here is CPU threads for those from the multi-threading world, the hyper-threading. It's because generally the terminology underneath is just CPUs, which isn't quite as misleading. So we've got 28 80-core systems coming. We already have a number of these arrived already. We've got two big memory systems. They've got 112 cores, up to a terabyte of RAM or 2 terabytes of RAM, depending on which system. And the biggest change is we're adding in modern NVIDIA cards. I don't think there's many of these already in Liverpool because they are pretty new. But we've got 6 of those cards across 3 systems, and they'll all be available within the platform. So for those, just to sort of summarize so far, so what is the big change that you're going to see? No fear, obviously, we're seeing the changes already with how we change the network and how we're interacting. You're going to start to see this project-based storage, which is very different to what you're seeing now, where I think it's been more PI-led. It's going to be, as a PI, for instance, if you have, let's say, 10 different PhD students, it's going to be a project each. And the idea for that is so we can manage the data, because we tend to lose track of what data is what. But the compute is probably going to be the most interesting. Because we're going to build applications on top of that, we're going to be able to start doing interesting things that allow you to work on your data back at your desk. So for example, if you're producing very big images, we're going to provide the applications where you can remotely get in and access those images with one of the 80-core systems backed behind it, or even more, or even all of the systems back behind it, depending on what you want to do. So that whether that is viewing the images, running something like segmentation, denoising, or any other technique. So just disclaimer at this point, my background is computer science. It is not imaging. It is not even biology. So there is going to be a mix of data that has been passed to me, and it may be EM, it may be LM. I've tried my best to figure out which is which, but I gave up. So just warning that there may be EM hiding in EM, possibly something else, who knows. But all of the prototypes are shown that this, or all the systems will show they're all prototypes at the moment. This all stuff we're working on, and hopefully stuff that we'll start to see over the next 12 months. So the first big one is desktops on demand. One of the requests we've had is when we come to processing this data, I'm trying to do it on my laptop, but I want to buy a big PC. And we can't keep buying a big PC for every individual person. That just kind of doesn't scale up very well. So one thing what we're aiming for is this desktop on demand. But the idea is if you produce your data with the facilities, you can then just request a desktop and you'll be able to process it. There's a very simple example with Cell Pores, which I imagine some people here use, is where you can request the desktop. Cell Pores will be available on it. It's web accessible, and you can just run that with the 80-core system hiding underneath. And then you'll be able to process it, but it's going to have direct access to the data you've already generated at the instrument. So you can pass that back and forth, and you'll be able to immediately pick it up as it's done. We're going to have a number of software as well. So this is not just going to be Cell Pores, there'll be all other tools. So we develop everything in-house. So if you want it and you think there's demand for it, we will build it. The other one which has been interesting is this ImageJ.js, which is a very much lightweight version of Fiji or ImageJ. The difference with ImageJ.js, if you've not come across it before, is it is built to run in a web browser. And the idea is all the data interactions are done server side. So instead of trying to open 2, 3, 4 gigabyte image that you've just generated, or several of them, you can open it on the server, but it's streamed directly to the web browser. Very similar to the desktops, but in terms of how that's built technologically, it's a bit different. But the idea then is you can pretty much generate your data, and the moment you walk out of the imaging facility, you can load that up on your iPad, and you can just start showing it. As easy as to describe that. So it doesn't matter how old your laptop is, how old your tablet is, you can just walk around and immediately start to show that and preview that. So this will be available immediately as soon as the data is across. And we'll support all the plugins as well, and we'll try to support as many of the plugins. If you want to do denoising, which is what this example is, then again, that will be available. The other one is deconvolution. So primarily the tools I've shown so far have been either GUI driven or web driven. We also support CLI tools, so where there is not a clear interface, it's a bit more intimidating when you've got to use a command line interface. We've been building web interfaces around command line tools as well. So in this case, we can get deconvolve as an example, and you can just see basically what this is doing, exactly what you would expect. But underneath this is a command line tool, just a web interface, and we can map that web interface again back to the previous tools I've just shown. So you'll be able to just preview your data raw, run it through a tool, and get the process data back. So just this data was only 27 frames, so quite a small data set. Ignoring the PSFs, that doesn't tend to change. In terms of the prediction, when you look at running this on, let's say, we use the term researcher workbench here, but what we really mean is a 4-core laptop or desktop. When we look at it and we just look at a simple prediction of that, we're talking a few minutes just for 27 frames. Well, say a few minutes, more along the lines of about 5 hours for a few frames versus running on the cluster, we're talking like 5 minutes. So the performance massively scales up. Which on that note, I was to go ahead to the next bit. So the thing that we really are interested in is large scale, and this is where the value towards maybe something like the CD7 comes in. It's not just about running software on a single node; it's about running software across multiple nodes. And we're doing really big runs. Like for example, this one, which was 7,560 frames, to run that through Cell Pose would be painful. To run each frame individually, clicking, and yeah, and that's just with that part. And then obviously the actual processing time is immense for this. Now we cheated a little bit to get this benchmark. We wrote a script to go around this rather than having an unfortunate student to click through buttons. That would be a bit cruel. And what we did is we compared that against running this on a single node and then running this on the cluster. And you can kind of see the scale here. So where if you're generating these massive runs, instead of taking, I think this works out as about 80 hours, if I remember off the top of my head, it's down to like an hour, if not less. And likewise, again, with deconvolve, this was a 700 frame image. It's an image I think you find when you wander around the facilities. It's Marie's award-winning image. Again, if you run this through a simple desktop, we're talking a few hours. But when we run across the cluster, it barely even gets on the scale. We're talking about 5 minutes versus 5 hours. So the idea here is that you can generate massive amounts of data, thousands of images, and we'll hopefully be able to process it in, I don't want to use the term real time, but in comparison, it is almost real time. Now, this is just the work we're doing for the CCI. These similar tools will start to appear for the EM unit as well. So this is going to be available across all facilities. So whatever data you generate, hopefully it'll be interactive. And I know some of the other facilities depend on MATLAB. So again, MATLAB will be available, whatever else is demanded. So just to bring that to an end, so in summarise, yep, we've got new storage coming and we've got a new compute platform coming. Part of that, we will be improving security and reliability, so that we're not depending on USB devices. So you'll probably start to see that inconvenience coming, unfortunately. I'm sorry, it's my fault. But hopefully that means that the systems will remain secure, let's say, reliable, and then we will start to make sure that the network is suitable, that you can get high-speed data straight across to the data storage. You can get that processed rapidly, and you can get that straight back out again. So Victor is here today and he's hiding at the back. Wave, goodbye. So Victor has been doing all of this work and has been doing an amazing job. If you have any questions about what is going on underneath, Victor will be happy to field as many questions as you want to ask him. He is a project student, so please make him suffer. Outside of that, obviously this data I've not generated. I couldn't tell you anything about it. So if anything looks exciting, please do speak to Maria or Marco. And other than that, obviously, I have to give an acknowledgement to IT services, but nobody ever does. Just to say they've done a fantastic job with trying to get some of the networking and infrastructure done for this project. Other than that, thank you very much.